Hey guys, welcome back to another edition. In geometry, it's Mr. Anderson here with you in section 5 today of chapter 10. We're going to talk about tangents. Okay, so let's get going. First of all, our objectives. We're going to use the properties of tangents. And number 2, solve problems involving circumscribed polygons. All right, so first of all, what is a tangent? A tangent is a line in the same plane as a circle that intersects the circle in exactly one point. So it's going to look something like this. I'm going to draw a little circle here the best I can, and then a tangent line will run like right through the edge of that. So something like that. That's actually really pretty good for doing that by hand. So this line is a tangent. It runs right and hits right on the edge of that circle. Okay, so next is a point of tangency. So if we're talking about the point of tangency, that's this one point right here where they intersect. So this right here is the point of tangency, right here where the line touches the circle. And then the other thing is a common tangent, and all that means is if you have two circles. Let's say you have two circles like this. That's really a horrible circle, but that you're going to draw, that you can draw a line or a tangent, a line that will be tangent to both of these at the same time. So for example, here we could draw one, something like that, more or less. And there are some other ones here too that we could do as well. And actually I'll get to that in the examples here, but anywhere we can draw a line that will intersect the edges of these circles would be considered a common tangent. And we'll look at a few of those in a second. So there could be more. Like, for example, on this one, I could also draw another one, you know, that goes maybe like this or something like that. All right, so let's take a look at a few examples here. All right, so first of all, draw the common tangents. How many common tangents are there? If no common tangent exists, state no common tangent. All right, so if you look at this, you want to look and see where could we draw a line that would intersect both of these. And instead of me trying to draw these by hand, I've got a handy dandy line here. Look at that. And so there would be one common tangent. It is tangent to both of these circles at the same time. What else? Oh, how about that one? So again, you could have one drawn that would be tangent to both these at the same time. In this situation, there is nothing else that we could do that would draw. We could draw a tangent that would intersect both of those. So that's all there is, and there would be two common tangents is what we have. All right. So we have two in that situation. All right. How about this one? This is kind of more like the example I was giving you, that I didn't want to give away everything because of this example here. So same thing here. We're just going to draw whatever common tangents we can. So there's one that we'd already talked about. You just can draw a line that goes across both of those. And earlier I drew one kind of like this as well. So there's the ones that we did. But can you think of any other ones? There could be a couple more here. And so if you look, you go, hey, what if I kind of drew a line somewhere in between there like that? That would be a common tangent because it would intersect here and here, but it's tangent to both of those. And there's one more just like that. Okay, so in that case, we've got four tangents that we can do there, four common tangents that we can do on that one. Okay? All right, next. All right, now this is kind of one of the most important things, a very important thing to remember about tangent lines. And so in a plane, a line is tangent to a circle if and only if it's perpendicular to the radius. All right, so from the radius to the point of tangency. So if it goes from the radius to the point of tangency, this has to be perpendicular, which means 90 degrees. Okay, so if the point of tangency is not 90 degrees from the tangent or from the line to the radius, if that's not a 90-degree angle, it will not be tangent. It is not tangent, okay? So keep that in mind. Let's look at a few examples there. All right, so here we've got a little drawing. We've got a triangle, basically, and a circle here. And what it's saying is, first of all, KL is a radius, so this is a radius. We want to know, is LM tangent to the circle? Is this line tangent? Well, what would tell us that that line was tangent? The only way to know that that would be tangent is if angle L was 90 degrees. So we say, well, that's what we're trying to do, is figure out, can we know for sure that angle L is 90 degrees? Well, if you look at that as the triangle there. There's something we know about triangles that we know we could get a 90-degree angle. So if you think about it, think about what we could do with a triangle and a right angle, and hopefully you said, hey, Mr. Anderson, I could do the Pythagorean theorem, and you would be correct. So remember, the Pythagorean theorem is a squared plus b squared equals c squared. And so remember, this only works for triangles that have 90-degree angles, right angles. And so if we put these numbers in here for A, B, and C, and they turn out to be equal, then we know it has to be 90 degrees, and therefore it's tangent. If it's not equal, if these two are not equal to each other, then it is not a 90-degree angle, and therefore not tangent. Okay, so let's plug these numbers in. Well, which angle would be C? Well, remember, or which side would be C? The angle that we're trying to prove that's 90 degrees is angle L. So if that's the one that we're trying to show is 90, that means that straight across from that would be C. So 29 would have to be the C here. So we're going to plug in 29. And then 20 and 21 would have to be these other numbers here. So this we have 20 squared plus 21 squared equals 29 squared. So let's see. Yay. Okay. Let's see if that's going to work. And so we do 20 squared plus 21 squared. Let's see what we get there. That's 841. So let's see, will this equal 29 squared? So 29 squared is 841. And so yes, those do equal each other, and there was much rejoicing. And so therefore we can say LM is tangent. Okay? To Circle K. By the way, have you ever heard of Circle K's before? It's like a convenience store in Oklahoma and probably other places. Let's go to the Circle K. All right, LM is tangent, though, because these are equal. Therefore, this is 90 degrees. And so, yes, it's tangent. All right, let's look at another one. Kind of the same setup. We're looking for the same thing. We're just going to plug it into the Pythagorean theorem. Remember, a squared plus b squared equals c squared. Again, the y is what we're trying to make 90 degrees. See if that's 90 degrees. So the c would be straight across from that. That's the 21. So in this case, the 21 is c. The 14 and the 16 are the a and the b. Okay, so that's what we're going to plug in. So here's our calculator. 14 squared plus 16 squared. So this time 452. And does this equal 21 squared? That one is 441. Oh, wah, wah. Nope, doesn't equal. And so in this case, we would say that in this case, YZ is not tangent to circle X. Okay, so hopefully you got an idea of what makes it look what it needs to look like to make it tangent and what it looks like when it's not tangent. So there you go. All right, now we're going to solve a few problems. It's very, very similar to what we've just been doing, but we're approaching it differently. So now what they're telling us here is the segments that appear to be tangent are tangent. So in other words, it's saying FG is tangent to circle E. And so what that tells us, when we hear that, we say, oh, that means this is 90 degrees. So we know now that it is 90 degrees. Okay, we're not trying to figure it out, we know. But what we're trying to find is, what's the missing value? In this case, x. Well, how could I do that? The Pythagorean theorem. Same exact thing that we did before, but we've got x to plug in. And so, again, let's look for which one is C. Here's the 90 degrees, look straight across from that. The 15 is your C. And so the other two will be your A and your B. So x squared plus 9 squared. Okay, so there's our formula. Let's work it out. X squared plus 81 equals, I don't know if I know that off the top of my head there, 15 squared, 225, minus 81. So x squared, should have just left that up, 225 minus 81 would be 144. And how do we undo squaring something? Take the square root. And so in this case, x squared of 144, do you know what that is? You might know this one. That's going to be 12. So in this case, x is 12. Now, what you could have done here as well, you know, we can always do the Pythagorean theorem here. But remember our Pythagorean triples, if you remember that from a few times back. So if you have 9 and 15, they can both be divided by 3. And so 9 divided by 3 is 3. 15 divided by 3 is what, 5? And so do you remember there was a Pythagorean triple that was 3, 4, 5? Remember 3, 4, 5? As a Pythagorean triple, 3, 4, and then 5. And so we would just, in order to get it back to the this length here, just since we divided by 3, then you just take that and multiply by 3, and there's your 12. So you notice, just like we did with the Pythagorean theorem. Okay, a little extra bonus learning there, no charge. Okay, let's look at one more like this. So same thing, it's telling us that WE is tangent. So it's tangent, which means this makes a 90-degree angle. The biggest thing to remember here, the thing that I've seen is the most confusing for people is making sure the right angle is 90 degrees. Did you get that? That the right angle is right. A lot of times what people want to do is they want to try to make this angle in here 90 degrees, okay? When we're talking about tangent lines, it's the angle out here at the edge of the circle that we want to be 90 degrees. That's the one that we're looking for, this one right here, okay? Not the one in the middle. Okay, so I just wanted to highlight that. All right, well, this one's a little bit different, though, a little bit trickier. That's why I saved this one. But if you notice, we've got a right triangle, just like we did before. And so we can do the Pythagorean theorem just like before. A squared plus b squared equals c squared. Okay, well, which one is C? Here's the right angle, look straight across from that. So this side is C, but you notice, you got x in here. That's the radius. From here to here is x, but then from here to here is 16. But I want to know what's the whole side here. What's that whole side? Well, what could we do? If we know this part's x and this part's 16, we could just call this x plus 16. Okay, just call it x plus 16. So that's C. And it's going to make it a little harder, but we can still do it. So we're going to plug that in for C, x plus 16 squared. And then here's our A and our B is x and 24. So x squared and 24 squared. Okay, let's see what we can do. We got x squared. Now we've got 24 squared. So 24 squared is 576. Ooh, okay, what do we do here? Now remember, this always fools people because they think, oh, I can do x squared and 16 squared. But remember, you've got a parentheses squared. Whenever we're squaring something, it means take it and multiply it by itself. So what I'm going to multiply by itself is x plus 16. So write it twice. X plus 16 times x plus 16. When you have two parentheses like this, what are we going to do? We are going to FOIL it. Okay? So x times x is x squared. That's this one. Outside, the first, f was first, x times x. Outside is x times 16, so we have 16x. Inside is 16 times x, another 16 times x. And then last would be 16 times 16. That would be 256. Okay, there we go. A little bit harder, but so far hopefully okay. Let's try to get like terms all together. So the first thing I notice, wow, first thing I notice is I've got x squared. So I'm going to go minus x squared minus x squared. Guess what? Oh, they all cancel out. That's nice. Okay. We got 16x and 16x. Well, we could make that 32x. Okay. Since this is being added, I'm going to subtract it. And so I've got what? 576 minus 256. 256. And so that looks like 320. Divide by 32. And we got x would be what? Oops. This is, there we go, 10. And that's what we were trying to find, was the value of 10 there. And so x is 10. All right, so a little trickier there, but that's something you can do when you run into a situation like that. All right. Now, if we have two tangent lines on the same circle, but they both go out to a common point, point B, they are congruent. So in this case, AB is congruent to CB. Those two lines are congruent to each other. Okay, it's pretty easy. Let's do an example here. So in this situation, it says AC and BC are tangent to Z. Circle Z, so they're tangent. Doesn't really look like it. It's not the best drawing there. But these are tangent, and they both go out to the same exact point. So therefore, what? That is congruent to that. And so our equation there would just be 3x plus 2 equals 4x minus 3. Just make them equal to each other. Let's solve it using algebra. And so minus 3x plus 3 plus 3. And so this just gives me x equals 5. And that's what we're trying to do, is find the value of x. Now, if you want to check yourself here, you could plug it back in. 5 times 3 is 15, plus 2 is 17. And then here, 5 times 4 is 20, minus 3 is 17. So that checks out. We're in good shape there. So x is 5. All right. Last one. A bouncy ball is marketed in a triangular package to pique the consumer's interest. If ABC is circumscribed about circle G, find the perimeter of ABC. So this is, remember we talked about inscribed and circumscribed. If something is inscribed, it's like inside the other thing, and usually the way we had it before was the triangle was inscribed maybe in a circle. Well, now the triangle is circumscribed. So basically, it's the triangle sits outside of the circle, and it has everywhere that it touches the edge of the circle and makes lines of tangency. Okay, it makes tangent lines, and so we have points of tangency is what I should have said. And so each one of these, point E, point D, and point F, are all points of tangency, and so each one of these lines is tangent to that circle. Okay, so think about the example that we just did. We want to find, well, we want to find the perimeter of ABC, so that's the distance all the way around. So all we have to do is think of each one of these like little vertexes, the vertices here, individually. So kind of cover up all this stuff here. Look just at this part here. A tangent line going out to a common point. What do we know about these two lines? They're congruent, right? If this is 6 centimeters, this will be 6 centimeters. So if this has to be 6, it tells us the whole thing is 16. So if this part right here is 6, what has to be left? 10. Well, now look at just this part down here. Tangent line, all go out to a common point. So these two have to be congruent to each other. So if this is 10, this will be 10. Over here, they told us that this was 12. And again, just look at this one. Tangent line, go out to a common point. So if that's 12, this has to be 12 here. And so all we have to do to find the perimeter here is just add all these up. So I'm going to have 12 plus 12 and 6 plus 6, that's these two, and 10 plus 10. All right. And so 12 and 12 is 24. 6 and 6 is 12. And 10 and 10 is 20. So altogether, that's going to be 56. And so this would equal 56 centimeters. Okay, so that's going to do it. A little bit about tangent lines and circles. So hopefully it wasn't too bad. Hopefully it makes sense. And, you know, appreciate you being here. Come back again next time. Next time we're going to talk about circles and the equations of circles. So we'll see you next time. This is Mr. Anderson saying so long. Bye.